Now that we have talked about mixed strategies, it's a time to talk about equilibrium using that mixed strategy. And the most obvious thing is the mixed strategy Nash equilibrium. The idea of mixed strategy Nash equilibrium is exactly similar as the pure strategy Nash equilibrium, just that we are now considering strategies which are probability distributions instead of pure strategies. So the definition formally goes as follows. We will call a strategy profile, a mixed strategy profile, sigma I star and sigma minus I star, a mixed strategy Nash equilibrium, if the following condition holds, that the utility of a player I at that strategy profile is going to be at least as much as the utility when that player is unilaterally deviating to sigma I prime, while all the other players are still holding on to their strategy sigma minus I star. And if this holds for all sigma I primes, which are in this set of all mixed strategies of player I, and if this inequality holds for every player, then we'll call that this sigma I star and sigma minus I star, this mixed strategy profile, is a mixed strategy Nash equilibrium. Now, the obvious question whenever we are introducing some new equilibrium concept is to connect that with the previous equilibrium concept. So what is the relationship between Psne and Msne? It is a time to pause the video and think about it. And if you have got the answer correctly, you know that Psne is actually equal, implies that it is also an Msne. So essentially, Psne is a degenerate mixed strategy Nash equilibrium, where the whole probability is concentrated at one pure strategy, and that is the Msne for that game. So if Psne exists, the Msne also exists, but there might be cases where Psne does not exist yet Msne exists. Let us also look at an alternative definition of mixed strategy Nash equilibrium. So just to give you a feel, we have looked at this sigma I prime. So we have talked about if your utility does not increase in any of the mixed strategies, which could be an uncountable set, then we'll call the sigma I star to be a mixed strategy Nash equilibrium. Turns out that you can actually relax that condition, and this is not without loss of it is without loss of generality. So what you can do is you can show that if you have a mixed strategy profile, this is going to be a mixed strategy Nash equilibrium if and only if the following condition holds. Note that all the inequality remains unchanged except the strategy has become a pure strategy. So it is saying that if you look at the utility of player I, when player I is playing a pure strategy and the other players are holding on to the mixed strategy of sigma minus I star, and if this holds for all SIs and for all players, this can also be considered as a equivalent definition of mixed strategy Nash equilibrium. So you can think of what this UI, so again we are overloading the notation a little bit. UI of SI sigma minus I is nothing but you are looking at the sum over all the S minus I's, which is living in this minus SI, and consider the joint probability distribution, so sigma minus I of S minus I, and then you have UI of SI S minus I. So whenever you are taking this weighted sum, that is exactly what we mean by this UI of sigma SI sigma minus I. Player I is playing a pure strategy, other players are playing a mixed strategy. So that is the thing which we have written on the right hand side. So it says that the expected utility of player I at that mixed strategy profile should be at least as much as this utility of player I for all strategies of player I. Right? The proof is not at all difficult, so let me just walk you through the proof. The forward direction, so, and we'll be denoting that as this. So in if and only if, this forward direction means that we start with the statement on the left, that is we consider that this sigma I star and sigma minus I star is a mixed strategy Nash equilibrium, and then we'll show that this inequality holds. So this also sometimes is called the only if direction. Now, because SI is a special case, so we are already given by the definition of mixed strategy Nash equilibrium. So by the definition of mixed strategy Nash equilibrium, we are going to the original definition here. So once that is given, SI is just a degenerate case of that. So you just put all the mass on SI. That probability distribution is going to give you the expectation, the utility that we have written on the right hand side. So from using the definition of mixed strategy Nash equilibrium, the forward direction is obvious. So there is nothing that needs to be formally proved in this case. The reverse directions is the if direction. So there we will be given this condition, and we'll have to show that sigma I star and sigma minus I star, this strategy profile, is actually a mixed strategy Nash equilibrium. So how should we do that? Let us pick any arbitrary mixed strategy for player I, sigma I. Okay, so and look at the utility that it gives to player I at the mixed strategy profile sigma I, sigma minus I star. So this is the that distinguished strategy profile of all the other players, sigma minus I star. Now, quite clearly we can write this down in the very same form. We know that how we have written the expression for ui si sigma minus I. So therefore we can expand that, and you will see that the expression that we have written for ui sigma I sigma minus I, you can equivalently write that with sigma I si multiplied by the utility of si sigma minus I star. Now what we are given, so is this part is essentially given to us. So we know that for every SI, sigma I star, so the utility of player I at the mixed strategy profile sigma I star and sigma minus I star is going to be at least as much as ui of SI sigma minus I. So without changing, and note that these are probability distributions, so these numbers are non-negative, so it will not flip the inequality. So for every such value, this inequality should hold. And now all that we need to do is to observe that this utility here and the sum on which we are taking this summation, that is over SI, and this utility sigma I star and sigma minus I star is not a function of SI at all. So this is, you can treat this as a constant and take this out, and the residual sum will only be on a probability distribution. So now you know that because of the property of a probability distribution, this is always going to be equal to 1. Okay, so this is going to be equal to 1, and therefore all that you are left with is just the utility at sigma I star and sigma minus I star. Now, because we have chosen this sigma I to be arbitrary and player I also to be arbitrary, you can repeat this exercise for any player or any strategy. Still, this ui sigma I sigma minus I star will be less than or equal to ui of sigma I star and sigma minus I star. And that is the definition of mixed strategy Nash equilibrium. And therefore, we are done. Let us look at some examples of mixed strategy Nash equilibrium. Let us go back to the original example of the penalty shootout game, and let's consider the same mixed strategy profile of player 1 and player 2. Now we are going to ask whether this strategy profile, according to the definition of the mixed strategy Nash equilibrium, is going to be a mixed strategy Nash equilibrium or not. So what we need to show to prove that this is a mixed strategy Nash equilibrium, we need to show that there does not exist any better mixed strategy for any of the players, either player 1 or player 2. Now what we can notice is that if we look at from the point of view of player 2, player 1 is mixing her strategy with probabilities 2/3 and 1/3. So therefore the expected utility for player 2, right, when player 2 is playing L, it is going to be 2/3 times the utility. So this number here, so player 2 gets this much utility when player 1 picks L and player 1 picks that with the probability 2/3. Similarly, gets -1 when player 1 picks R and player 1 picks R with probability 1/3. So therefore, you can look at do this math and find out that the expected utility is 1/3. Now, you do the similar exercise when when player 2 is considering to play strategy R, then it is going to be -1/3. Now you can clearly see if player 1 or player 2 moves some amount of probability mass from R to L, it is going to get better off, because the utility when player 1 is picking this mixed strategy profile, it is always beneficial to move to L. Actually, there is no reason to play R, because that is going to give him less expected utility than playing L. So clearly this strategy profile where player 2 is dividing the probability mass between L and R with 4, 5 and 1, 5, that is never going to be a mixed strategy equilibrium, because player 2 has a profitable deviation from it. You can do the similar exercise for player 1 and you can also find that there is a profitable deviation. So this strategy profile 2/3 by 2/3, 1/3, 4/5, 1/5 is not a mixed strategy Nash equilibrium. Now do the same exercise for this mixed strategies, this mixed strategy profile. Here the mixed strategy profile is that player 1 is choosing both these strategies with probability half, and similarly player 2 is also choosing this strategies with probability half. Can you find any strategy profile, mixed strategy or pure strategy profile that can improve on this?